Good afternoon. Last class we were discussing the exact solutions of Navier-Stokes equations, and we appreciated the fact that in certain special cases of steady, incompressible, laminar, fully developed flow, the Navier-Stokes equation is converted to ordinary linear differential equations. This is because of the fact that the inertial terms, the left hand side of the Navier-Stokes equation, identically vanishes. So therefore, it is possible to have a closed form solution by integrating the resulting Navier-Stokes equations, and we have already discussed a situation like Couette flow. Today we will discuss plain Poiseuille flow. We will discuss, and it is very simple when we have discussed the Couette flow, so it will automatically come. The plain Poiseuille flow, first of all we have to define what is plain Poiseuille flow. This is the name of a scientist, is a great person in fluid mechanics. So this flow is like this. This is again a steady, incompressible, laminar, fully developed flow between two plates which are stationary. That means two fixed plates. In Couette flow, one of the plates was moving with a velocity relative to the other, so that the flow was caused by shear, at the same time pressure gradient if it is imposed. But here, since the two plates are held stationary, the flow takes place only by virtue of the pressure gradient. So in this case, if we remember that if we take the axis like this is our x, this is our y. Now, since by geometry of the flow, this is symmetrical with respect to the central line, because the two plates are at rest, the identical kinematic boundary conditions. So therefore, it is convenient to use this as the axis x at the central line, y and z. Now in general, we have already developed that in Cartesian coordinate system, for these situations of exact solutions, our Navier-Stokes equation becomes d square u dy square. This already we appreciated, 1 by mu dp dx. V0, w by definition 0, there is no velocity in the z component, and the width of the channel is so large compared to this spacing or the height, and here we define this as h, total spacing, that the change of any parameter with respect to z is negligible compared to x and y. So with all these assumptions, we have found that u is a function of y only and p is a function of x only, and this is the equation resulting from the x direction Navier-Stokes equation. And since p is a function of x and u is a function of y, they are constant. All these things were derived the last class, and if we integrate it, we get du dy is 1 by mu dp dx y. All these things we did earlier, plus c1, and the next one is that u is equal to 1 by 2 mu dp dx y square plus c1 y plus c2. So therefore, any such situation of steady laminar fully developed incompressible flow. This is a common equation with respect to a Cartesian coordinate system in general. So, C1, C2 will change according to the definition of flow by its geometry. So, plane Poiseuille flow is specified by the two fixed plates. So, therefore, our boundary conditions will be at y is equal to plus minus h by 2, that means at two walls h by 2 and minus h by 2, since we have taken the x-axis along the center line. Clear? No slip condition demands u is equal to 0. Since the flow is axisymmetric about this center line, okay, then we can write at y is equal to 0 du dy 0, and this comes from the physical sense that it is symmetry, and if we take this type of axis, that means plus h by 2 minus h by 2, we have the same results, which means that C1 has to be 0 mathematically at y 0 du dy 0. That means there cannot be any term containing the first power of y. And if we put this boundary condition, we get C2 is equal to h minus 1 by 8 mu, I write h square by 8 mu minus, this is a style of writing, minus dp dx. So, C2 becomes h square by 8 mu minus dp dx. So, if you substitute this C2 here, finally you get the velocity profile like this, h square by 8 mu, you take this as common, minus dp dx into 1 minus 4y square by h square. If you just put the value of C2 here, then you get this equation. And it can be written in a form like this, which looks better, dp dx into 1 minus y square by h by 2 whole square. That means square of the half height or half spacing of the channel. Okay. So, this is the u. Now, it is clear from this equation that u is maximum. Now, one thing, before that one thing, you see that if dp dx is 0, u is 0 here, unlike the coed flow, because here the flow is driven by the pressure gradient and it is known as pressure driven flow, and it is at the same time apparent that the sign of dp dx and u are consistent. If you have a negative pressure gradient, that means pressure decreases in the positive direction of x, which is known as favorable pressure gradient. That means the pressure force on a fluid element acts in this direction, positive direction. Pressure upstream is high, downstream is low, and in that case u is positive. And accordingly, the reverse is true, that dp dx is positive, that when the upstream pressure is, downstream pressure is more than the upstream pressure, which we call as adverse pressure gradient. When the pressure force on a fluid element is in the direction opposite to the positive direction of x, in that case this causes a velocity in the negative direction. That means flow is solely governed by the pressure gradient and is known as pressure driven flow. Now, the maximum velocity occurs at y is equal to 0, and whose value is, now it may be maximum, minimum, the way you define it. If it is in the negative direction, you call it a maximum, minimum, and it is the positive direction with dp dx negative, you call it as a maximum. And accordingly, you see that du dy, d square u dy square sign depends upon dp dx from the first governing equation. If dp dx is negative, d square u dy square curvature as in, that means velocity has a maximum. And if dp dx is positive, d square u dy square is positive, that means velocity has a minimum. So, it is a question of sign convention, but the value of u max is this. So, sometimes we can write that u by u max, this is another way of representing, is 1 minus y square by h by 2 whole square. This is the velocity distribution. The next task is to find out the volumetric flow rate, Q. Now volumetric flow rate, to find out, I have told you earlier that if I take a small element dy here, and if you consider its width as b, a small element like this, a cross sectional plane, that means if you see this view, it is like this. It is like this. This is dy and this is b. That means if we consider a small element of height dy and width b, then through that the flow rate is u into b dy. That means the value of u prevailing at that particular y, at that particular y, at that particular y, at that particular y, at that particular y. Now if you put this expression of u there, and if you integrate to minus h by 2 to h by 2, that means across the channel height, then you get a relationship like this, that is h cube by 12 mu, h cube b by 12 mu into minus dp dx. That means you just substitute this u and simply you integrate with y. This will be dy, this will be y squared dy, y cube by 3, and accordingly you get this expression. Now here one thing I like to mention very much, which is not written in any book. I don't know that whether how many books have written it. Now volumetric flow rate is usually a scalar quantity, but if you deduce this way, we come across with minus dp dx. So if you think of the sign of dp dx, because dp dx is pressure gradient, it must have a sign. So dp dx is either negative or positive. That will indicate whether pressure is increasing or decreasing in the direction of flow. So therefore q indicates a sign, but it is better in my opinion to write q as h cube b by 12 mu, the absolute or mod value of dp dx. I take only its value, and this represents a scalar quantity flow rate across a section. U average as average velocity in fluid flow is defined by the volumetric flow rate. That means for internal flow through a duct is defined as volumetric flow rate divided by the cross sectional area. And if you do that, cross sectional area is b into h, then you get h squared by 12 mu mod of dp dx. Of course, here you can put that minus dp dx type of thing to show the direction of u average, which will be inconsistent with the direction of u. But if you think this way, that average flow velocity I will consider as a scalar quantity. It is a cross-sectionally average based on the volume flow rate, and which will simply represent the value whether in the distribution u, local velocity, will have its sign accordingly with the sign of dp dx. So therefore you can keep this intact to show the u average as a scale of the q, that is volumetric flow rate, which is a scalar quantity. So it is simply h square by 12 mu dp dx. And if you see, compare it with u max, then we can write that u average is 2/3 of u max, 2/3 of u max. Clear? Now the next task for us is to find out the shear stress at wall. Now shear stress here takes place in the direction of x at any plane which is perpendicular to y, whose normal is in the y direction. So tau xy, from a general relation we know mu into shear rate or rate of angular or shear strain in xy plane, that is del v del x plus del u del y. But at this moment this is not necessary, because we know everything here, that there is no v component and u is a function of y only, du dy. So therefore tau we can write let us consider tau at y is equal to minus h by 2. Now what is du dy? Du dy is this one. Du dy is C1 is 0, 1 by mu dp dx into minus h by 2. So therefore it is 1 by mu du dy, mu is cancelling each other, okay, h by 2 into minus dp dx. H by 2 into minus dp dx. If you put this value y is equal to minus h by 2. Now tau at the upper wall y is equal to h by 2 is what? H by 2 into dp dx. This is the value of shear stress at two walls. The value, numerical value is the same because of the symmetry. But about the sign, you see one thing, that here first let us consider a flow taking place in the positive direction, u positive. Then what is dp dx? Dp dx is negative. So if dp dx is negative, so tau at the lower plate is positive, that means in the x direction, whereas tau at the upper plate is negative in the opposite direction. True from these two equations, but physically it is not so, because the flow takes place in this direction. This is the flow direction. This is the flow direction. So shear stress at the lower plate is acting in this direction, and the shear stress on the upper plate should act also in this direction. So where is the problem? Where is my confusion? This is because the coordinate, yes, the upper plate implies a tau xy is opposite to that. A positive tau xy is in the opposite direction, because this is a plane where the normal is the negative y, not the positive y, correct? I think this thing has been emphasized by Professor Suman Chakraborty. When you specify the sign of a stress, it is at second order tension, so it has two signs. One is this direction, another is the plane specifying the direction, outward normal. So but the normal, outward normal is in the negative y direction, and that's why this sign convention is there. So with this thing, now I will go to the most important parameter of any fluid flow analysis with which engineers are mostly interested, is the drag on the surface, solid surface, for external flow and for internal flow. For internal flow it is most important, because it is the shear stress at the solid surface that determines the pressure drop. That already you have learned your basic fluid mechanics class. So therefore shear stress at the solid surface is very important, and this defines a scalar quantity known as coefficient of friction. Coefficient of friction, CF. I have already told earlier, probably in one occasion, that it is defined like this: half rho u average square. I already defined it earlier so far, if I recall, that a friction coefficient in case of internal flow and drag coefficient in case of external flow is the representation of dimensionless wall shear stress or plate shear stress, surface shear stress, which is defined as the shear stress, its absolute value, because this is a scalar quantity divided by the dynamic head based on the reference velocity, which is u average in the present case. Present case means the internal flow, it is the average velocity. For an external flow, it is the free stream velocity. Now if we find out this one, then you get tau w is equal to h by 2 dp dx. Now if you substitute the dp dx from the average velocity, if you substitute dp dx mod from the average velocity, then you get 12 mu average velocity. It is equal to h by 2 into dp dx, that means 12 mu by h square, 12 mu by h square into U average. This is the, and if you substitute this, H will cancel and substitute this, you get an expression 12 by Reynolds number, where this Reynolds number is represented as rho U average H by mean. In any internal flow, the Reynolds number is defined based on the average velocity and hydraulic diameter, which in this case is the height between the plates. And this CF is known as Fanning's friction factor. Fanning, Fanning friction factor. Fanning friction factor. This is all about the plane Poiseuille flow. So it is very simple up to this. This is common. This is a generic equation, C1y plus C2. From there, the geometry of the flow will allow. That means after this, what happens is simply the algebra. There is no fluid mechanics, and you have to understand the sign conventions according to the algebra. Okay, clear? Now we will discuss another situation of exact solution, which is more important than plane Poiseuille and Couette flow in engineering practice, is Hagen Poiseuille flow. Is Hagen Poiseuille flow. Incidentally, these two are the name of the two scientists, Hagen and Poiseuille, like Bose and Einstein, Bose-Einstein theory. Bose-Einstein is not a same person, two persons. So that people know since his birth, since his or her birth. But this is fluid mechanics without thermofluids people do not know. Hagen and Poiseuille, they are very famous top personalities in the field. What is a Hagen Poiseuille flow? Again, I am telling you, it is a steady, incompressible, laminar, fully developed flow through a cylindrical duct, through a tube, through a pipe. That's why it is very common in engineering practice. That means in a duct with a uniform circular cross section throughout. But the flow is fully developed. The growth of boundary layer from the surface merges at the axis and steady, laminar, incompressible. But the geometry is that it is a circular tube. That means it is now if we analyze the flow through a tube, through a duct with circular cross section, it is always convenient to use the cylindrical coordinate system, cylindrical polar coordinate system. And in cylindrical polar coordinate system, a point here is represented by its three coordinates. One is the R, and the central line is considered to the line at R is equal to 0. And to represent this point in a cylindrical polar coordinate system, we have to see the cross-sectional view of this duct. And if you see this cross-sectional view, it will be better. That means this point comes here, and this is our radial coordinate. And with respect to any preferable direction, this is the theta that you already know, and Z is the third dimension perpendicular to this plane. That means in this view, this is Z. That means its Z is considered some Z is equal to 0 plane, you consider this Z. Its Z location is this. That means R theta Z is the coordinate of the point. So theta is the azimuthal coordinate, r is the radial and z is the axial coordinate. Now, after specifying the coordinate system, fluid mechanics stops here, only mathematics. Why? This is because this flow is a fully developed flow. Before that, by the geometry of the flow, it is axially symmetric or azimuthally symmetric. That means it is symmetric with respect to r is equal to 0, which we call as an axis symmetric or azimuthal symmetric flow. And this type of flow, where the boundary conditions are also symmetric, because around the entire cylindrical surface at all values of r, it is a no slip condition valid u0. That means it is azimuthally symmetric, which can be mathematically written as del del theta of any parameter is 0. Of any parameter, this comes first from the definition of the problem. That means the problem is azimuthally symmetric, for which the r is equal to 0 is taken as the central axis. Okay. Next is the fully developed flow, and this fully developed flow condition, as you know, that del Vz, del Z is 0. That is the requirement of fully developed flow, that Vz ceases to be a function of Z. I have told earlier also, it is function of r only, because there is no dependence on theta. So therefore the consequence is that Vz is a function of r only. Well, now let us write the continuity equation. Let us write the continuity equation. Now continuity equation for an steady incompressible flow, as you know, that divergence of the velocity vector is 0. And in a cylindrical coordinate system, I write the divergence is, as you know, is del del r ijk if Vr V theta. Now I have to define Vr. Vr is this in the r direction. Vz is along the z direction and V theta is along the theta direction. So therefore, this is 1 upon r del del theta j plus del del z k, and V, the velocity vector, is defined as Vr ijk are the unit vector in theta plus and Vzk. Now this is a preliminary vector calculus. This becomes 1 upon r del del r of r Vz. This has been told in your fluid mechanics class. RVR plus 1 upon r del V theta del theta plus del Vz del z. That means it is counterpart of del u del x plus del v del y plus, it is the counterpart of del u del x plus del v del y plus del w del z 0. So this is the continuity equation. If we invoke the continuity equation, this is 0 because V theta is absent. The flow is defined with V theta 0. There is no tangential component of velocity. It's not that only del del theta of any parameter is 0, but tangential component of velocity is absent. But both the cases that this term is 0. Then del Vz del z by the definition of the fully developed flow 0. So we have then the only option, that means this equation tells this is 0. Okay, which means that del del r of RVR is 0, which means that, what is that meaning? That RVR, no, just a minute, del del r of RVR, exactly, that means RVR is 0. Why? This is because similar way we obtained that del V del y 0 means V 0, because impermeable boundary. So if you apply this RVR from this point and go for each and every point in the flow, you get the RVR 0. You understand me? That means del of any del y, for example, here a del r of any parameter is 0, means that parameter is 0 provided this boundary conditions tell that two surfaces or along the surfaces this is 0. That means it will have 0 velocities in the entire field. So this is a mathematical consequence, and this has to be understood like that. If you put that condition at the surface, so you see that the immediate next point, immediate vicinity to that surface has to be 0 if that gradient is 0. So that way next point will 0. So it cannot initiate any value. Mathematically, it means that the field itself is 0. You understand? But if the surface, any one of the surface, here it is a single surface, but in case of two plates, if one of the surface is permeable, there is a suction or blowing, then this is not true. That means even if this change with the y is 0, the field is not 0. Clear to everybody? So the similar way we obtain that del v del y 0 v 0, RVR 0 means next step RVR 0, VR is equal to 0 except a singularity at the axis where r is equal to 0. That singularity I will show you how to tackle with the velocity distribution equation. So therefore we get that VR 0, V theta 0 and Vz is a function of r only. Now you see that since del p del theta 0 and there is no theta component of velocity, I don't want to invoke or call the Navier-Stokes equation in theta directions. It is unnecessary. It is not required. You can see in your book how it is written. Now in art direction equation also, in absence of Vr and V theta, will give you del p. There cannot be a pressure gradient. If you expand, because in this short time I don't want to write it, this remains as your task, that probably it has been taught earlier, that if you expand the Navier-Stokes equation in art direction, you will see in absence of Vr and V theta, del p del r will be 0. This is similar to the Couette flow or plane Poiseuille flow in Cartesian coordinate, del p del y is 0. That means cross gradient is 0. And it is very easy to physically understand, since there is no velocity in the art direction and no azimuthal velocity, no pressure gradient can exist. The question of azimuthal velocity comes because of the tangential velocity, a radial pressure gradient is created, which is responsible for the centripetal acceleration and the centripetal force. So probably those things have been taught at your fluid mechanics, basic fluid mechanics class. So therefore in absence of Vr V theta, there cannot be any radial pressure gradient. So del p del r is 0 and already parameter with respect to theta is 0, del p del theta 0, we wrote it earlier. The consequence, this p becomes a function of z. It is in the similar line we did with the Cartesian coordinate system for plane Poiseuille and Couette flow. Then I recall or invoke the art direction equation, Navier-Stokes equation. What is that? Rho dvz dt is equal to minus del p del z plus mu of Laplacian Vz. Now I expand this for clarity, this temporal derivative, though it is not required. You can tell, sir, we know that a steady flow temporal derivative is 0. However, for the clarity, then Vr del Vz del r plus 1 by r, rather V theta by r del Vz del theta plus Vz del Vz del z del Vz del z equals to minus del p del z plus mu del square Vz. Now if we split this, I think it is better to write in a compact form like this. This again, if you follow the vector algebra with this notation of del in the cylindrical coordinate system, it is again the vector algebra that del del r 1 by r, sorry, 1 by r, if you write, it is mathematics only, del del r, r del vz del r plus 1 by r square del square v theta del theta square plus del square vz del r square. That means it is counterpart of the Laplacian in Cartesian coordinate del square u del x square plus del square v del y square, sorry, del square u del y square plus, sorry, this is vz plus del square u del z square. So it is the counterpart of that, so it is in cylindrical polar coordinate system. Now we know, first come here, the steady flow 0. We see how the z direction equation motion, the inertial term identically vanishes. V are absent, v theta absent, and here though vz is there, but del vz del z 0 because of fully developed inertial term vanished. Now already it is proved that p is a function of z, so it should be written in terms of ordinary differential equation. And here also there is no dependence with theta for azimuthal symmetry, and there is no dependence with del z square. There is no dependence with z, del square vz del z square. So only this term remains, and also here I can replace this term as d, that means ordinary differential equation. That means from here what I get 1 by r ddr of r dvz dr is equal to 1 by mu dp dz. From this equation I get this. I think it is okay, so that I can finally get from all three Navier-Stokes equations in three directions r theta z this equation, the way we obtain for Cartesian coordinate systems also, for plane Poiseuille and Couette flow. Now it becomes simple mathematics integration. Since vz is a function of r and p is a function of z, the equality holds good for a constant, which means from here only the logic tells that p is a linear function of z and u is a quadratic function of r. So that equality holds good, they become constant, that the second derivative of vz with respect to r and first derivative of p with respect to z becomes constant. Okay, all right. Now you integrate it. The first integration goes ddr of this, that means r dvz dr equals to, you just multiply with r and integrate, that means r square by 2 mu dp dz plus c1, and then next one is dvz dr is r by 2 mu dp dz plus c1 by r, and the next one is vz is r square by 4 mu dp dz plus c1 ln r plus c2. And here also the boundary conditions are at r is equal to r, vz 0. We have two constants. Another boundary condition is the azimuthal or axis symmetric boundary condition, which means dvz dr at r is equal to 0, rather you write in the same fashion, r is equal to 0, dvz dr is 0. dvz dr is 0. Okay, and this automatically tells that this equation cannot have a term like this. ln r is, that's why I told that this will be tackled, that singularity at the center at r is equal to 0 will be tackled automatically by allowing this c1 to be 0. so that this term vanishes. And similarly in the dvz dr term, this term cannot happen to have a singularity. So therefore this term will not come at all, and this becomes symmetric about r is equal to 0. And if you put that, you get C2 is equal to capital R square by 8 mu, sorry 4 mu, I am sorry 4 mu into minus dp dz. This is my technique of writing always, minus dp dz, to show that plus minus should be associated with dp dz, to have an understanding with the favorable and the adverse pressure gradient depending upon the situations. Okay. Now after this, our routine task is like this. We find out the maximum velocity. The maximum velocity at r is equal to 0 obviously, and that is equal to r square. Oh, I have not yet written this Vz. Then if you substitute this C2 here, then you get the Vz r square is similar to Poiseuille thing, 4 mu into minus dp dz into 1 minus r square by r square. The remaining part at school level thing, that Vz maximum, that is Vz at r is equal to 0, that is r square by 8 mu into minus dp dz 4 mu into minus dp. Why I am writing 8 mu? 4 mu into minus dp. So one can express Vz by Vz max as 1 minus r square by r square. So therefore the Poiseuille flow like this. Similar is the Poiseuille flow. This is the distribution of velocity for various pressure gradients. So minus dp dz. So therefore flow is purely driven by the pressure gradient, pressure driven flow, where dp dz is negative, flow is positive, dp dz is positive, flow is negative. That means in the opposite direction. Next task is what? Next task is tau w, which is tau rz. First of all, let us write tau. That means shear stress in the direction of flow, which is in the rz plane. At any plane parallel to the flow, that is rz plane, which can be written as mu into corresponding rate of angular or shear strain, that is del Vz del r plus del Vr del z. This has been taught at your basic fluid mechanics class. Since in this case Vr is not there and Vz is a function of r, therefore tau is mu dVz dr. Well, therefore tau is mu dVz dr. Tau is mu dVz dr. So therefore tau rz in this case is mu dVz dr. Now rest part is very simple and routine. So tau w is nothing but tau rz. Now let us find out tau rz, mu dVz dr. What is dVz dr? So if you find out dVz dr, it will be, now let us find out this also. Tau, it is r twice r square is cancelling, r by 2 mu into dp dz. Tau rz is r by, that means you get dVz dr from here. I have rubbed this, dVz dr was there in the solution. So dVz dr if you make, then you get this value, that tau is equal to r by 2 mu. You get 2r, 2 cancels, and 2 mu r square. Oh, mu also will not be there, r by 2, very good, r by 2 dp dz. There is no mu. Clear? So therefore, tau w, that means r by z. What is tau w? Tau w is equal to tau rz at r is equal to r. That becomes is equal to r by 2 into, and here again the same understanding that dp dz negative gives a positive flow, and shear stress physically acts in the positive direction, but it gives a negative value mathematically because the plane is tau rz negative, because r is downward. Very good. Okay. So similarly, if you write the friction coefficient as this, half rho, before that I have to find out Vz average. Sorry, I have not found out the Vz average. Before that I have come to the shear stress. Now let us find out average velocity or volumetric flow rate. Volumetric flow rate, again volume average flow. In case of a plane geometry, the volume average flow is simply the arithmetic average. But here the volume average flow, to find out, we have to consider a elemental area, annular area with thickness dr at a radius r, thickness dr, which is represented here like this. This is the dr in this diagram, which is an annular ring with thickness dr. That means therefore the area is twice pi r dr, the area of the annular ring is twice pi r dr, and this is written as u into dA, that is twice pi r dr. So this is the volumetric flow rate, u into dA. Here dA is annular area twice pi r dr, and this integrated 0 to r, and you get a value of this pi r4 by 16, 8 mu into minus dp dz. That means if you substitute this distribution, sorry, I am extremely sorry, this will be Vz. So if you substitute this Vz expression here, and you get pi r4 by 8 mu minus dp dz. And to represent the q, you can express this as the modulus of this. That means q can be expressed as pi r4 by 8 mu. I think this is more reasonable to understand because volume flow rate has no sign, and Vz average therefore is equal to, then divided by the cross sectional area, that means r square by 8 mu into dp dz, which is Vz max by 2. Now I come to the coefficient of friction, the same way as I did earlier for plane Poiseuille flow. If you define the coefficient of friction Cf as tau w by half rho Vz average square, and if you use this tau Vz average from here, if you dp dz, if you tau w is r by 2 dp dz, so if you substitute tau in terms of dp dz and dp dz in terms of the Vz average as I did earlier, then it becomes equal to 16 by Reynolds number, where Reynolds number in this case is defined as rho Vz average 2r by mu. I don't want to spend time in such small school level calculations, that I tell you that tau w is r by 2 dp dz. Here it is dp dz, you can use the modulus of that, which will be again substituted in terms of Vz average. so that tau w will come in terms of Vz average, rho will be there, and this thing is denominator. Ultimately this will give, this is a Reynolds number defined on the basis of the diameter 2r, diameter of the cylindrical duct, which is the hydraulic diameter, as you know, which is defined as 4 cross-sectional area divided by the 4 times the cross-sectional area divided by the weighted perimeter, and this comes out to be the diameter 2r, rho, and average velocity mu is the dynamic viscosity. So here I end this discussion on Hagen Poiseuille flow, but at the end I like to tell you one thing which I ignored from the beginning. Whenever I write the Navier-Stokes equation, it is del P del X, del P del Y, or del P del Z. What is this P? You know, P is the piezometric pressures. So in all books, in my book also you will see that people use P with a star. I think Professor Suman Chakraborty has told, when the Navier-Stokes equation was derived, we got rid of the body force terms. There is no body force we consider except gravity, and we write the pressure gradient. But gravity as the body force we can never neglect. We may neglect other body forces which are otherwise not imposed. Some electric field, some magnetic field may not be imposed on it, but gravity is there. So gravity we never write as a body force. For example, in a vertical flow, in a vertical direction, y direction equation, the gravity will come. Or in an inclined flow, inclined plane, you have seen that liquid flowing, so gravity. So that gravity is taken into account by piezometric pressure. This has been told, it is a very preliminary knowledge at your basic fluid mechanics class. So all this P, what I have used, you consider this as a piezometric pressure. That's why in books usually it is written as P star. You will see in many books it is written, and in my book also P star. So the pressure here which I write in the Navier-Stokes equations, for example, if I write the Navier-Stokes equation, for example, just this is for your concept, forget that exact solution is over, that when the Navier-Stokes equation is written, let us write in a very compact vector form, minus grad of P, P star. Actually here we will not use star, we will read P as the piezometric pressure, plus mu, forget about the next term, mu by 3 grad of, that is not required, mu by 3 grad of del dot P. This is term for the compressibility. If incompressible flow, this is 0. But this P star is known as piezometric pressure. What is this piezometric pressure? I think you know it takes care of the static pressure plus the gravity equivalent pressure, not H. Z, where Z is coordinate in the direction of gravity, it is elevation or whatever you can from a reference datum. For an example, when I told that the imposed pressure gradient, for an example like this, when this type of problem you have done earlier, just for your concept I tell you, for an example, if there is a inclined plane and a liquid film is flowing, and this plane is inclined by an angle theta. So if you take a fluid element, now pressure here is all atmospheric at this and this, if this is section 1 and this is section 2, P1 minus P2 is 0. So then what causing the flow is the gravity. That means the component of its weight in this direction. And that is the difference of the piezometric pressure force. That means in that case the piezometric pressure difference, P star at 1 minus P star at 2 will be rho g Z1 minus Z2. And that time area, if you multiply here cross-sectional area, you get the effective gravity. That means if you define a cross-sectional area A, and if you define here this is Z1, and if you define here this is Z2, then you will get this equation. That means if you define this as length, so the effective gravity, that is W sine theta, that means this is in this direction, W sine theta, which is causing the element to come, liquid to flow, and that is given by this rho g, Z1 minus Z2 into the cross sectional area will be the pressure force. That means when we deal with this type of very simple equation at the very fundamental stage or the basic stage, preliminary stage of studies, we don't think of that piezometric pressure. We simply make the force balance, that the gravity is pulling this, and if the shear force in the liquid at the wall balances the effective gravity, then the film flows with the constant or uniform velocity. So therefore, this gravity is taken in terms of a piezometric pressure, where rho g z, the gravity equivalent pressure, is there. So therefore, all these Navier-Stokes equations, without any imposed body force from outside, implies the pressure as the piezometric pressure. When we deal with flows in horizontal plane, then the delta P is equal to delta P star. That means the difference of piezometric pressure and difference static pressure is same. So therefore, we can read it as simply static pressure. Okay. So any question? All right. So next class we will start the boundary layer theory, a brief introduction of the boundary layer theory, recapitulation rather. Many of you have already read it earlier in your fluid mechanics class, and that will be taken by Professor Sumon Chakraborty. Okay, thank you.